As an exercise, consider the following system of two linear algebraic equations. 2x1 plus 3x2 plus x3 is 0, and 3x1 plus 2x2 plus x4 is 1. If we have two or three unknowns, we usually denote them xy or xyz. If we have four or more unknowns, then xyz stop and the alphabet stops there. Then we usually use x1, x2, x3, x4 and so on. Well, once again, we use the matrix notation and we use Gauss elimination. So we write the matrix 2, 3, 1, no x4, so that means coefficient is 0, and on the right you have 0, and the second equation translates to the second row, namely 3, 2, 0, 1, 1. So this is the augmented matrix of the system, and we want to transform this to the upper triangular form. We have now 0 here, so we can copy the first row to get 2, 3, 1, 0, 0. And to get 0 here, we take 2 times the second minus 3 times the first will be the new second row. And we have 6 minus 6, which is 0. And we do the same operation with the remainder of the second row. And we get 4 minus 9, which is minus 5. Minus 3, 2, 2. So this was the Gauss elimination, and the matrix is in the upper triangular form. We don't have to stop here. We can use Gauss-Jordan elimination, and we can bring this square block not just to the upper triangular form, but even to the diagonal form. That means we want to have zeros not only below the main diagonal, but also above. That means we don't like this number 3. And we can get rid of this 3 by taking 5 times the first row, and we add 3 times the second. And we do this for the entire row. So we can copy the second row, 0, minus 5, minus 3, 2, 2. And here we have 5 times the first, which is 10. 15 minus 15 is 0. That was the reason for this combination. And we continue. 5 minus 9 is minus 4, and 6, and 6. Well, and this is a nice result. And once again, this matrix can be divided into 3 parts. We have the right-hand side column. This is the column for its own. Then on the left, we have the square block in the diagonal form. This is the best form that we can get. And then we have some columns in the middle. Well, and now considering the variables corresponding to the columns in the middle part, we can assign any value, any parameter for these 2 variables. So if we write that the first column corresponds to x1, this to x2, x3, x4, then we can write that x4 may be any real parameter, any number for the moment. And so can x3. But we should choose a different letter, right? Say u. T and u may be any real numbers. And then compute x1 and x2 in terms of these two parameters. The second row actually corresponds to an equation 0 times x1 minus 5x2 minus 3x4, which is x3, which is u, plus 2x4, which is t, is equal to 2. And we can express x2 if we move these two terms to the right and if we divide by minus 5. So we have 2 minus 2t plus 3u divided by minus 5. And similarly, the first row corresponds to the equation 10x1 minus 4x3, which is u, plus 6x4, which is t, and this is equal to 6. So we can conveniently find x1 if we move these two terms to the right and we divide by 10. So we have fraction 6 minus 6t plus 4u divided by 10. And this is the complete general solution. T and u may be any real numbers, and then x1, x2, x3, x4 are given by these four expressions. These two unknowns can be written as a vector. And we can write these four expressions, namely, and let's write it as 6 over 10, which is 3 over 5, minus 3 over 5t, plus 2 over 5 u, that is x1. x2 is minus 2/5 plus 2/5 t and minus 3/5 u. And x3 is u alone and x4 is t alone. And this can be still reformulated by first writing the absolute terms with no parameter. This is 3 over 5 minus 2 over 5, 0, 0, plus, and now consider the terms with t. And we can write the parameter t times the vector of coefficients, minus 3/5, 2/5, 0, 1, and what remains are the terms with u. And similarly, we can factor out u and write the coefficients alone. 2/5 minus 3/5, 1, 0. Because this form allows a nice geometrical interpretation. The set of all the solutions forms one natural geometrical object. Which one? If it were just this column, nothing more, then it will be a fixed point in some four-dimensional space. If we have a point plus parameter times a vector, that will correspond to a line, one-dimensional line in this four-dimensional space. And when we take this point and when we move in this direction or in this direction or any combination of them, this generates a plane, a two-dimensional plane in this four-dimensional space. And these two vectors can be considered two directional vectors of the plane. Let us discuss in more detail the dimension of the set of the solution and the number of parameters and the properties of the equation. Imagine this four-dimensional space. So we have some vector x1, x2, x3, x4. If we have no equation at all, or if we have equations in the form 0 is 0, which is equivalent to having no equation, because this represents no information, no restriction, no condition. If we have no equation, then the dimension of the space of the solution is 4, or in general n, the number of unknowns. If we have one equation, imagine just this one, nothing more, then one equation, that means different from 0, consumes one direction, and the dimension of the space of the solution is just 3. If we have two equations like here, the dimensions will be 2. If we have 3 independent equations, then the dimension will be just 1. That means a line. If we have 4 independent equations, that was for 4. And if we have more equations than unknowns, then no solution. Sorry. So that was for no equation, 1 equation, 2 equation, 3 equation. If we have 4 equations, then we have just 1 point. That means the dimension is 0. You can think of the dimension as the number of parameters. And if we have more equations than unknowns, then we have no solution at all. So we can say that the dimension of the space of the solution, the number of parameters, is the number of columns in this middle part. And if we have n unknowns, and if we have rank of A, in this case 2, then rank columns here, n columns here. So the number of columns in the middle part is n minus rank. And for the system to have a solution at all, the rank of the matrix must be equal to the rank of the augmented matrix. So the more equations we have, the lower the lower the dimension of the set of the solution. That means adding more equations means restricting the dimension, the number of degrees of freedom, the number of independent directions that you can move. So this is the number of parameters or the dimension of the set of the solution, which is equal to the number of unknowns minus the number of important equations, which is the rank of the matrix A.